Welcome to homework.
36.34 is about these rings you can see around the moon at night when there is fog or sort of very wispy clouds that don't just sort of block the light. So you should go out and sometime when the moon is out, you can look for these things because they're sort of nice to look at. There's a picture in the book also, but it's better in person. Um, But basically, this is caused by water droplets in the air acting as obstacles, producing diffraction patterns. We saw earlier with a problem uh, 16, I think. Um, we explained something called Babinet's principle, which means that the diffraction pattern of an aperture is the same as for an obstacle with the same shape as the aperture, sort of its complement, if you will. So the water droplets block light and produce the same diffraction patterns that they would if they were little circular apertures of the same size. And so you see sort of a total effect of all of these when you look at the moon. And now the question wants us to answer some things about this. I mean, the question is mainly just a very long description of the phenomenon, and then the actual uh, parts of it are not very involved, which is why I have nothing written down here. So the first is, what is the color of the rings that you see around the moon? At the outside of each maximum? So for this, we just look at uh, our equation here for, so the outside of the each ring, or each sort of set of rings. First of all, the colors separate because each one gets diffracted by, each wavelength is diffracted by a different amount. Um, and then each sort of spread out ring of color represents one sort of peak in the thing, and we're looking at sort of the central maximum. So you're going to see sort of one of these for each color, and so they have sort of a cumulative effect together. And the angle at which they'll have their sort of last visible portion is given by this, the Rayleigh criterion. And so we can see that the angle will increase as lambda increases, which means that the outsides of the rings, which have larger angles, of course, correspond to longer wavelengths. And so the outside of each ring will be red, and then the colors end up sort of overlapping too much further inside of the ring to really uh, make out anything but sort of whitish light. But around the edges of each ring, you can see the red color. So for part B, the ring around the central maximum in the picture in the book that you can go and look at has an angular diameter that's 1.35 times that of the moon, which is half a degree. So we want to know what the diameter of the water droplet is. So here our theta is, first of all, we need to convert it to degrees. So we have 2 pi radian, or I'm sorry, we have to convert it to radians. So we have 2 pi radians over 360 degrees. And then we want half of this, because this is the angular diameter, and we just want the angle from the normal here. So 1.35 times 0.5 degrees divided by 2. And so then the diameter of a droplet is 1.22 times the wavelength divided by theta. Now, we said that the red light is going to be on the outside, and that occurs around 700 nanometers. So that's what we're going to use for our lambda here. And so we get 1.3 times 10 to the negative 4th meters is the approximate diameter of one of our little water droplets.